Look at Orion on a clear winter night, and the sky seems to offer something almost comforting. 3 stars in a straight slanting line, a bright blue foot, a second bright shoulder, and above the belt, glowing with a color that is not quite red and not quite orange, a star people have named for centuries, mispronounced for generations, and recently turned into a cosmic rumor. Betelgeuse. It looks quiet. It looks like a point. It looks like one more ornament pinned to the dark. That is the first lie. The light entering your eye from Betelgeuse is not a live signal. It is an old message, already centuries out of date. Depending on which distance estimate you accept, you are seeing the star roughly 500 to 700 years in the past. The Betelgeuse above your roof is not necessarily the Betelgeuse that exists now. It is the Betelgeuse of another human era. A star as it was while empires changed hands, languages shifted, ships crossed oceans, and nobody on Earth had any way to know that the red point in Orion was a dying giant. Astronomy always asks us to accept this strange humiliation. The sky is not a place we observe in the present. It is a museum of delayed arrivals. And that delay matters because Betelgeuse is not simply large. It is unstable in the deep physical sense of the word. It is a red supergiant, a star near the final chapters of a short, violent life. If it were placed where the Sun is, the inner solar system would not orbit it. The inner solar system would be inside it. Mercury would vanish into its atmosphere. Venus would be buried. Earth would not be warmed by its light. Earth would be part of its outer envelope. Mars would be swallowed too. And depending on which radius model is closest to the truth, its atmosphere could stretch into the asteroid belt or even toward Jupiter's neighborhood. The numbers are uncertain because the star has no clean surface. It is not a hard ball. It is a boiling, breathing atmosphere fading outward into space. But the uncertainty does not make the star ordinary. It makes it stranger. We cannot measure its edge perfectly because the edge is not a simple thing. The popular story says Betelgeuse is frightening because it might explode tomorrow. That is the easy version. It is also the weaker one. The real argument is more uncomfortable. Betelgeuse matters because it forces us to confront the difference between spectacle and mechanism. We want the universe to give us events, a flash, a date, a headline, a bright new object in the daytime sky. But the universe is not a news cycle. Betelgeuse is not a countdown timer placed there for human excitement. It is a physical system revealing a harsher truth. The same mass that makes a star magnificent also makes its life shorter, more unstable, and more violently creative. The debate is not whether Betelgeuse will die. It will. The debate is whether we understand what its dying actually means. There's a tempting way to tell the story. A huge star is about to explode. The sky is warning us. The dimming was a sign. The red shoulder of Orion could vanish at any moment. This version has drama, but it treats uncertainty as permission to exaggerate. The stronger version is quieter and more dangerous. Betelgeuse may explode in a few thousand years, or in 100,000 years. Or perhaps the explosion has already happened, and the light has not reached us yet. We do not know. And that is not a failure of imagination. It is a boundary of measurement. We can watch the surface of the star pulse and darken and brighten. We can measure its spectrum. We can map huge cells of hot gas on its face. But the fatal clock is buried in its core under hundreds of millions of miles of star. So the thesis of this story is not that Betelgeuse is a threat to us. It is too far away to sterilize Earth. It will not burn our atmosphere or rain catastrophe onto our oceans. The thesis is that Betelgeuse is a challenge to the way we think about cosmic safety. We feel safe because the star looks calm. We feel informed because we know it is going to explode. But both feelings are incomplete. Betelgeuse is calm only because distance smooths violence into beauty. And we know its fate only in the broad sense, not in the human sense that asks when, exactly, the final second will come. The star is not a monster waiting for us. It is a witness against our habit of turning deep time into a schedule. Begin with scale, because every other part of the story depends on it. The sun already defeats ordinary intuition. From Earth, it appears as a disk you can cover with a thumb. But that tiny disk is about 1.39 million kilometers across. More than 100 Earths could be lined across its diameter. Over 1 million Earths could fit inside its volume. The sun contains almost all the mass in the solar system. It holds planets, asteroids, comets, and dust in a gravitational arrangement that has remained stable enough for life to appear on one small rocky world. And yet the sun is not a giant by stellar standards. It is a stable, middle-aged, main-sequence star. Impressive to us, ordinary to the galaxy. Betelgeuse turns that baseline into a toy. If its radius is about 700 times the sun's radius, then its diameter is around 1,400 suns across. Because volume grows with the cube of radius, the difference becomes almost absurd. A star only 15 or so times the sun's mass can occupy hundreds of millions of times the sun's volume. That contrast tells us something essential. Betelgeuse is not a dense ball. It is inflated. Its outer atmosphere is so thin and extended that a sharp boundary is almost the wrong idea. The star is more like a luminous storm than a sphere, more like a red fog held loosely by gravity than the clean drawing of a star in a textbook. This is why different sources give different apparent sizes. The star is variable. Its atmosphere moves. It sheds material. It has large, uneven surface structures. Its diameter depends partly on the wavelength used to observe it, and partly on where one decides the star ends. A planet has a surface. A red supergiant has a transition. There is no cliff where star stops and space begins. There is a fading, a thinning, a border that breathes. From the outside, that sounds like a technical problem. In fact, it is the first scientific warning. Stable objects tend to have well-defined boundaries. Betelgeuse does not. It is leaking itself into space. It is losing mass through a wind far stronger than anything the sun produces. It lifts material from its interior through enormous convective motions, throws gas into its outer atmosphere, allows that gas to cool, and sometimes turns it into dust. The star is not simply shining, it is shedding. That shedding became famous during the Great Dimming of 2019 and 2020. For months, Betelgeuse faded so dramatically that ordinary observers noticed the change with the naked eye. Orion looked wrong. The familiar shoulder was suddenly weak. Headlines did what headlines do. They asked whether the star was about to explode. The public imagination rushed to the most cinematic conclusion. A dying supergiant had dimmed. Perhaps the final collapse was beginning. But careful astronomy told a different story. High-resolution observations showed that part of the star had been obscured by dust, likely connected to a surface event, a large ejection of gas, a cooler patch on the photosphere, and dust condensing close to the star. In other words, the dimming was real, but its meaning was not the one people wanted. It revealed how red supergiants lose mass. It revealed how turbulent and irregular Betelgeuse's outer layers are. It did not prove that the core was about to collapse. This distinction matters because it is the heart of scientific caution. A dramatic observation is not automatically a dramatic conclusion. A star can dim for reasons that happen near its surface, while the decisive processes happen far deeper down. The surface is what we see. The core is what decides the future. Betelgeuse teaches us that the universe can give us a visible symptom that feels like a warning and still not be the warning we imagined. There is a counter-argument worth taking seriously. If a red supergiant is so unstable, and if it is already near the end of its life, perhaps unusual dimming events do have some connection to the final state of the star. Perhaps the surface is not completely disconnected from the interior. Perhaps mass loss, pulsation, dust formation, and late-stage burning are all parts of one larger disequilibrium. That objection is reasonable. Stars are not machines with neatly separated compartments. They are fluid bodies, gravitational systems, nuclear furnaces, and extinct and turbulent atmospheres all at once. Surface behavior may carry information about the interior in ways we have not fully decoded, but there is a limit to that argument. No established model allows us to look at one dust event and say, with confidence, that core collapse is imminent. The final nuclear burning stages are hidden. The last fuel stages unfold under conditions we do not directly observe. Until the neutrinos arrive, or until the light of the explosion begins, the surface cannot give us a precise countdown. Betelgeuse may be late in its life. That does not mean every flicker is a death rattle. To understand why, we have to leave the surface and follow the logic of mass. A star is a compromise between collapse and resistance. Gravity pulls inward. Nuclear fusion pushes outward. For most of the Sun's life, that balance is steady because hydrogen fusion in the core produces enough pressure to resist gravity. The Sun burns slowly because it is not excessively massive. Its core is hot enough to fuse hydrogen, but not so hot that it races through its fuel in a cosmic instant. It can spend about 10 billion years on the main sequence. Massive stars do not receive that luxury. A common intuition says that a star with more mass has more fuel and should therefore live longer. The opposite is true. More mass means stronger gravity. Stronger gravity compresses the core to higher temperatures and pressures. Higher temperatures make fusion proceed much faster. The fuel supply increases, but the rate of consumption increases far more sharply. A massive star is not a bigger candle. It is a bonfire with extra wood thrown in after the flames are already roaring. Betelgeuse was probably born as a hot blue or blue-white massive star in the Orion region, only several million years ago. That alone is astonishing. The Sun is about 4.6 billion years old and still in midlife. Betelgeuse, at perhaps around 8 to 10 million years old, is already elderly. If the Sun's lifespan were a long human life, Betelgeuse would be a creature that appears in the morning and dies before the day is done. Its mass gave it brilliance, and brilliance spent its life. During its main sequence phase, Betelgeuse fused hydrogen into helium in its core. In massive stars, hydrogen fusion is dominated by the CNO cycle, a process extremely sensitive to temperature. A small rise in core temperature can drive a large increase in energy production. This is efficient in the moment and ruinous over time. The star shines with immense luminosity, but it pays for that luminosity by burning through its fuel quickly. When the core hydrogen was exhausted, the core became helium ash. Fusion in the center paused. Gravity tightened its grip. The core contracted and heated, while hydrogen in a shell around it ignited. That shell burning poured energy into the outer layers, pushing them outward. As the star expanded, its surface cooled and reddened. The blue massive star transformed into a red supergiant. This is the bloated object we see now. The word giant can mislead us. It suggests strength. In stellar evolution, swelling is often a sign of crisis. The star has not grown because it is healthy. It has grown because its internal structure has changed. The core is moving through fuels faster and faster. The outer envelope is responding by expanding, cooling, pulsating, and leaking mass. Betelgeuse's size is not a triumph. It is a symptom. After hydrogen comes helium. At about 100 million degrees, helium nuclei can fuse through the triple alpha process to form carbon. For a star like Betelgeuse, helium burning lasts far less than hydrogen burning. Then, if the star is massive enough, carbon can ignite, then neon, then oxygen, then silicon. Each stage demands a hotter core, and each stage lasts less time. Hydrogen burning lasts millions of years. Helium burning might last around 1 million years. Carbon burning could last thousands of years or less, depending on the star. Neon and oxygen burning can last years or months. Silicon burning, the final stage, can last only days or less. The sequence is not a gentle aging process. It is an acceleration. The star is not simply running out of fuel. It is moving through worse fuels faster, shedding stability as it goes. Each new stage produces less usable energy per unit mass than the one before it, while the core loses more energy through neutrinos. These ghostly particles escape from the core almost freely, carrying energy away. The star has to burn faster to hold itself up, and burning faster brings it closer to the end. Eventually, the core becomes iron. Iron is the betrayal at the center of massive star evolution. Up to iron, fusion releases energy. That released energy supports the star. But iron sits near the peak of nuclear binding efficiency. Fusing iron into heavier elements consumes energy instead of releasing it. The star has reached a nuclear dead end. There is no next fuel that can save it. The iron core grows as silicon burning adds more iron from above. The core becomes heavier and more unstable. Gravity waits. The crucial limit is not emotional. It is mathematical. Electron degeneracy pressure, a quantum mechanical resistance arising from the Pauli exclusion principle, can hold up a compact core only up to a certain mass. That limit is about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. Below that, electrons can resist compression. Above that, gravity wins. In a massive star's iron core, once this threshold is crossed, collapse begins. And when it begins, the star does not negotiate. The core falls inward at a significant fraction of the speed of light. Something roughly Earth-sized collapses toward the size of a city in less than a second. Electrons are driven into protons, producing neutrons and neutrinos. Matter is compressed to nuclear density. A teaspoon of the resulting material would weigh billions of tons. The collapse halts when neutron degeneracy pressure and nuclear forces resist further compression, forming a proto-neutron star. Infalling material slams into this stiff core and rebounds, launching a shock wave outward. At first, the shock seems as if it should simply blow the star apart. But the real physics is more subtle. The shock loses energy as it pushes through the dense material above the core. It can stall. For decades, this was a major problem in supernova theory. How does the shock revive? The answer, in broad terms, involves neutrinos. The core collapse releases an enormous flood of neutrinos. Most escape, carrying away the vast majority of the gravitational energy. But a small fraction deposits energy behind the stalled shock. That small fraction of a colossal reservoir can be enough to revive the shock and drive it outward. The outer layers of the star are expelled. The red supergiant becomes a supernova. The violence is almost impossible to scale honestly. A core collapse supernova releases most of its energy as neutrinos in a burst lasting seconds. The visible light, the part humans would celebrate, is only a tiny fraction of the total. Yet even that fraction can make one star rival or outshine the combined light of enormous stellar populations for a brief time. The debris races outward at thousands of kilometers per second. The layered onion of the star is torn open. Hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, sulfur, iron, and newly formed heavier elements are thrown into space. This is where the story changes tone. Supernovae are not merely deaths. They are distribution mechanisms. They are how the galaxy receives many of the ingredients needed for rocky planets and complex chemistry. The oxygen in air, the silicon in rocks, the calcium in bones, the iron in blood, and many heavy elements in technology and geology are tied to earlier generations of stars and stellar explosions. The universe did not begin rich in these materials. The early universe was mostly hydrogen and helium with a trace of lithium. The rest had to be made. So Betelgeuse is not just a doomed giant. It is a chemical furnace, approaching the moment when its contents will be returned to the galaxy. Its death will be destructive locally and creative broadly. This is the uncomfortable duality at the heart of the account. We want to call the supernova an ending because we identify with the star as an object. But from the perspective of galactic evolution, the supernova is also a method of inheritance. A star dies. Future worlds become possible. There is a real counter-argument here. And it should not be brushed aside with sentimental language about star stuff. Not every heavy element comes mainly from ordinary core collapse supernovae. Neutron star mergers are now known to be major factories for some of the heaviest R-process elements, including much gold and platinum. Different elements have different origins. Some are made in massive stars before explosion. Some are made during explosive burning. Some are made in thermonuclear supernovae from white dwarfs. Some are made in neutron star collisions. The slogan, "We are made of supernova," is broadly true in spirit, but too simple in detail. That correction does not weaken the story, it strengthens it. The chemical universe is not produced by one kind of catastrophe, but by a network of stellar deaths. Betelgeuse belongs to one part of that network. Its future explosion will not single-handedly create all complexity, but it will inject processed material into the interstellar medium. It will enrich its neighborhood. It will join the long chain of stellar recycling that made rocky worlds possible in the first place. Now return to the question people ask most urgently. When will Betelgeuse explode? The honest answer is not satisfying, and that is why it is important. It will explode soon in astronomical terms. Soon may mean within the next 100,000 years. Some models suggest it could be much sooner, perhaps within thousands of years. If the star is further along in its burning sequence than conservative estimates assume. Other models place it earlier in the late-stage evolution, leaving more time. The disagreement is not because astronomers are careless. It is because several key inputs remain uncertain: mass, distance, rotation, mass loss, internal mixing, and the exact evolutionary stage of the core. The public often hears "within 100,000 years" and laughs because the number feels meaningless. But for a star only several million years old, 100,000 years is not vast. It is a final fraction. To a human life, it is an abyss. To Betelgeuse, it is a narrow ledge. This mismatch between human time and stellar time is one of the reasons the star fascinates us. It is both imminent and distant, both nearly done and not necessarily relevant to any person alive. There is another complication. Because Betelgeuse is hundreds of light years away, when has two meanings. There is the moment the core collapses at the star, and there is the moment the information reaches Earth. If the star exploded in its own frame today, Earth would not know until centuries from now. If Earth sees the supernova tomorrow, then the explosion already happened centuries ago. This is not wordplay. It is the structure of observation in a universe with a finite speed of light. We do not observe cosmic now. We observe arriving pasts. This makes Betelgeuse feel like a sealed envelope already in transit. Perhaps the envelope contains an ordinary red supergiant still burning late-stage fuel. Perhaps it contains the news of a collapse that has already occurred. The only way to know is to wait for the signal. Astronomy is patient because it has no alternative. What signal would arrive first? Not light, neutrinos. During core collapse, neutrinos escape from the stellar interior far more easily than photons. The photons from the explosion must push through the star's enormous envelope before the shock breakout becomes visible. Neutrinos stream out almost immediately. In a nearby galactic supernova, detectors on Earth would see a sudden burst of neutrinos before the visible light appeared. This is not speculation. In 1987, when a star exploded in the Large Magellanic Cloud, neutrino detectors saw a small burst hours before the optical brightening was observed. Only a handful of particles were detected, but those few particles confirmed an entire theoretical picture. A core had collapsed, and a neutrino flood had crossed space. Today, the world is better prepared. Networks of neutrino detectors are linked through early warning systems designed to alert astronomers when a galactic core collapse begins. If Betelgeuse collapses, instruments could warn observatories before the first light breaks out from the star. For the first time in human history, telescopes across the world and in orbit could turn toward a nearby supernova before it becomes visible. We would not merely notice the explosion, we would watch it begin. That scientific opportunity is staggering. We have observed many supernovae in distant galaxies, and we have studied the remnant of SN 1987A in detail. But a supernova as close as Betelgeuse would be a different class of event. Every wavelength, every neutrino detector, perhaps gravitational wave observatories if conditions allow, every major telescope would become part of one planetary instrument. We would test core collapse models with a precision impossible for faraway explosions. We would observe shock breakout, early spectra, debris expansion, dust formation, remnant formation, and the birth of a neutron star or possibly a black hole. From Earth, the view would be extraordinary but not dangerous. This is another place where the story must resist exaggeration. Betelgeuse is close for a supernova, but not close enough to threaten life. The danger zone for serious atmospheric damage from a supernova is usually discussed in tens of light years, not hundreds. Betelgeuse is far beyond that. Its neutrinos would pass through our bodies, and the planet almost entirely unnoticed. Its light would be brilliant, perhaps comparable to the full moon in apparent brightness, perhaps visible in daytime depending on details. But brightness is not the same as danger. The radiation would spread across space before reaching us. It would transform the sky, not sterilize Earth. This is a better kind of awe. The event would be safe enough to watch and powerful enough to change the cultural memory of our species. Imagine Orion altered. For weeks or months, the shoulder of the hunter becomes a dazzling point, visible even when the sun is above the horizon. At night it casts a pale light. Children learn a sky their grandparents never saw. Astronomers barely sleep. Amateur observers make sketches. Satellites and telescopes record spectra and light curves. Poets reach for metaphors and fail. Then the brightness fades. The supernova becomes a remnant. The familiar red star is gone. Orion, one of the oldest patterns humans have named, carries a missing shoulder. The sky reminds us that constellations are not eternal architecture. They are temporary human drawings imposed on moving, changing, dying stars. Historical memory gives us a taste of what such a moment can mean. In the year 1054, astronomers in East Asia recorded a guest star visible in daylight for weeks. Today we identify the remnant as the Crab Nebula, with a pulsar at its center spinning about 30 times per second. In 1572, Tycho Brahe observed a new star bright enough to challenge ancient beliefs that the heavens were unchanging. In 1604, Kepler observed another. These events did more than brighten the sky. They cracked a worldview. They showed that the heavens were not perfect and permanent. They could change. A Betelgeuse supernova would do something similar for the modern world. Not because it would surprise physics in the basic sense, we expect it, but because expectation is not the same as witnessing. We know stars die. Seeing one of the most familiar naked-eye stars vanish into a supernova would move that knowledge from abstraction into memory. It would make stellar evolution visible to the unaided human eye. And yet we must return to the argument that prevents this from becoming mere spectacle. The most interesting thing about Betelgeuse is not that it will give us a show. The most interesting thing is that the show is only the final visible consequence of a deeper mechanical chain. Mass set the path. Mass raised core temperature. Core temperature accelerated fusion. Fusion built heavier elements. Iron ended the chain. Collapse followed. The supernova is not a random disaster. It is the price of being a massive star. That price was written into Betelgeuse from birth. There is a controversy hidden in this fact. Not a scandal, but a philosophical pressure point. In ordinary language, we often describe stars as if they choose a life cycle. They are born, they live, they die. But the more closely we study them, the less room there is for narrative freedom. A star's initial mass heavily determines its fate. Small red dwarfs hoard fuel and can live for trillions of years. Sun-like stars live billions of years and fade into white dwarfs. Massive stars burn brightly and die catastrophically. Betelgeuse did not become unstable because it failed. It became unstable because the conditions that made it luminous also made long-term stability impossible. This is where the debate becomes human, even though the physics is not about us. We admire brightness. We associate scale with strength. We call the largest things powerful. Betelgeuse argues the opposite. Extreme brightness can be a form of fragility. Enormous size can be a symptom of internal crisis. The star that dominates a constellation may be closer to death than the faint red dwarf no one notices. The quiet, small, fuel-saving stars may outlive almost everything. A science-literate observer might object that fragility is an emotional word. Betelgeuse is not fragile in any ordinary sense. It is a massive astrophysical system, and its structure is governed by robust physical laws. Calling it fragile risks projecting human vulnerability onto plasma. That objection is fair, but the word is not meant to imply weakness of material. It points to the narrowness of the balance. A red supergiant is sustained by linked processes that change rapidly near the end: shell burning, mass loss, convection, neutrino cooling, core contraction. Compared with main sequence stability, it is a transitional object. Its vastness is real, but it is not permanent. The more exact claim is this: Betelgeuse is stable enough to exist now, but not stable enough to remain what it is. Its current state is temporary, late, and dynamically active. That is stronger than fear and more honest than comfort. What makes Betelgeuse especially valuable is that we can study it in unusual detail. Most stars are points of light even in powerful telescopes. Betelgeuse is one of the rare exceptions. Its angular diameter is large enough, thanks to its size and relative proximity, that interferometry can resolve its disk. More than a century ago, Michelson and Pease used an interferometer on the Mount Wilson telescope to measure its angular diameter, a landmark in stellar astronomy. Modern interferometers and space telescopes have gone further, imaging surface asymmetries, hotspots, dust, and changes over time. That fact should be more famous than the rumor of explosion. Betelgeuse is a laboratory for the late lives of massive stars. We can watch a red supergiant shed material. We can track its brightness cycles. We can study giant convective cells. We can observe how dust forms close to a dying star. We can test how mass loss works before core collapse. These are not minor details. Mass loss can shape the final supernova. The amount of envelope remaining affects the light curve, spectra, and remnant. The surface chaos is not merely decorative. It is part of the pre-supernova story. Recent evidence for a possible companion star adds another layer. A long secondary cycle in Betelgeuse's brightness has puzzled astronomers for years. An observation suggests a smaller companion may be moving through or near the star's extended atmosphere, leaving a wake in the gas. If confirmed and fully understood, this would remind us again that massive star evolution is not always a clean single-star problem. Companions can shape mass loss, rotation, circumstellar material, and observed variability. The star may be famous as a singular object, but it may not be evolving in isolation. This is an important counterweight to overly neat storytelling. A simple account says Betelgeuse is a dying star, and all its changes come from its final countdown. A more careful account says the visible behavior may involve pulsation, convection, dust, mass ejection, and possibly companion interaction, while the core's evolutionary stage remains uncertain. That is not less exciting, it is more realistic. Nature often hides decisive causes under overlapping effects. The question of distance illustrates the same problem. Betelgeuse is bright, nearby in astronomical terms, and famous, yet its exact distance has been difficult to pin down. Parallax measurements are complicated by its enormous size, changing surface, and extended atmosphere. Different studies have placed it at different distances, often in the range of roughly 500 to 700 light-years. Distance affects luminosity. Luminosity affects inferred radius and evolutionary state. A few hundred light-years of uncertainty may sound embarrassing for a famous star, but it is not a simple point source. It is a moving, swollen atmosphere with structure. The more precisely we look, the less it behaves like the idealized object our methods prefer. This is part of the deeper lesson. Scientific uncertainty is not always ignorance in the lazy sense. Sometimes uncertainty is the honest imprint of a complex object on limited measurements. We do not know Betelgeuse perfectly because it is difficult, not because astronomy has failed. Now imagine the star in its final day, though the actual final day may be nowhere near ours. Deep in the core, silicon burning produces iron. The iron core grows. Outside it, Shells of oxygen, neon, carbon, helium, and hydrogen continue burning in nested layers. The outer atmosphere remains vast and turbulent, unaware in any immediate sense that the core is approaching a threshold. Then, electron degeneracy fails. The core collapses. Neutrinos burst outward. The shock wave forms and stalls and is revived. The star tears open from within. From the inside, it is an almost instantaneous catastrophe. From Earth, it is a message delayed by centuries. From the galaxy, it is one more enrichment event in a long chemical cycle. From a future planet that may one day form out of the debris, it is not catastrophe at all. It is ancestry. That shift in perspective is the emotional core of the story. The same event can be death, data, danger, beauty, and inheritance, depending on the scale from which it is viewed. Betelgeuse is not one story. It is a junction where multiple stories cross. To the human eye, it is a red point in Orion. To an astrophysicist, it is a red supergiant with uncertain parameters and rich variability. To a nuclear physicist, it is an onion of burning shells approaching the iron limit. To a neutrino detector, it will be a sudden burst of ghost particles. To the interstellar medium, it will be a delivery of processed elements. To future astronomers, it will be a remnant. To future chemistry, it may be raw material. This is why the simplistic fear of Betelgeuse exploding tomorrow is too small for the subject. It reduces the star to a cosmic firework. The real object is far more profound. It is a reminder that creation in the universe often works through instability. Planets need heavy elements. Heavy elements need stars and stellar deaths. Life needs chemistry, and chemistry beyond the simplest elements needs earlier generations of violence. We are not separate from these events. We are downstream of them. There is an uncomfortable consequence in that. If the processes that make life possible are violent, then the universe is not designed around comfort. It is not a nursery. It is not a machine built to keep delicate things safe. It is a system in which delicate things can arise temporarily because earlier violent processes prepared the materials. Betelgeuse is not threatening us directly, but it reveals a universe where beauty and danger are not opposites. They are often the same process seen at different times. This is the argument a careful documentary should make. Betelgeuse is not scary because it will kill us. It is unsettling because it shows that our existence depends on stars that do not survive their own brilliance. The atoms that make stable life come from unstable histories. The calm night sky is built out of ancient catastrophes. If there is a counter-argument to this broader claim, it is that we are giving too much symbolic weight to one star. Betelgeuse is not unique. It is one red supergiant among many. It may not even be the next visible supernova in our galaxy. Other massive stars could explode first, hidden by dust, or placed elsewhere in the Milky Way. Turning Betelgeuse into a cosmic symbol risks making it more special than it is. That objection is correct scientifically, and still the symbol is justified. Betelgeuse matters not because it is unique in the galaxy, but because it is accessible to human senses. It is near enough, bright enough, large enough, and culturally familiar enough to connect stellar evolution to naked eye experience. There may be more extreme stars, more massive stars, more imminent candidates, but few sit so visibly in a constellation known across cultures. Few allow the human eye to touch the late life of a massive star without a telescope. Betelgeuse is not statistically unique. It is pedagogically rare. The next question is what would happen to Orion after the explosion. In the first days, the new light would dominate. Over weeks, It would fade from its peak. Over months, the spectacle would decline. Over years, the location would become less dramatic. Over centuries, a remnant would expand, accessible to telescopes as a growing nebula. The star that defined the shoulder would be gone from naked-eye astronomy, replaced by a compact remnant hidden in debris. The hunter would lose part of his shape. Constellations are human inventions, but that does not make their loss meaningless. Humans have used the sky as memory. Orion has been a seasonal signal, a mythic figure, a navigational pattern, a winter companion. A supernova would make visible what astronomy already knows. The patterns we treat as ancient and stable are temporary alignments. Stars move. Stars vary. Stars die. The sky is not fixed. It is slow. The slow sky is difficult to feel because human lives are short. Betelgeuse compresses that difficulty. It is both ancient to us and young to the galaxy. It is both stable across recorded human history and unstable in stellar terms. It is both a point and a volume that could engulf planetary orbits. It is both safe and violent. It is both not about to harm us and not going to last. This tension is exactly where the documentary voice should live. Not in panic, not in reassurance, in the space between them. Consider the phrase Betelgeuse is getting close. Close to what? Close to supernova in astronomical time? Yes. But not necessarily close in human time. Close to the end of a massive star pathway? Yes. But not predictable in the way a clock on a wall is predictable. Close enough for scientists to care deeply. Not close enough for anyone to mark a date. The word close is both true and dangerous. It needs context. Scientific language often loses observers because it removes drama. Popular language often misleads observers because it removes uncertainty. The stronger path is to make uncertainty dramatic. The unknown timing is not an inconvenience. It is the point. We are watching a system whose end is physically inevitable and temporally hidden. That is more haunting than a fake countdown. It also reveals something about our relationship with prediction. Humans are comfortable with uncertainty when it is small and scheduled. A storm forecast gives a day. A medical test gives a probability. An eclipse gives a second. Betelgeuse gives a mechanism without a date. It says, the ending is certain, but the arrival of the message is not. That kind of knowledge is difficult to hold. It is neither ignorance nor certainty. It is a suspended fact. The suspended fact is this. Somewhere in Orion, a red supergiant is burning through the last architecture of its life. It may still have many thousands of years. It may not. Its surface will continue to breathe, darken, brighten, and shed dust. Its hidden core will continue along a path we infer but cannot directly watch. One day, the core will decide the surface's fate. The decision will happen in less than a second. The announcement will cross centuries of space. When the announcement arrives, Earth will not need protection. It will need attention. There is a strange kindness in that. Many cosmic events are either too faint to notice or too dangerous to wish for. Betelgeuse's supernova sits in a rare category, close enough to transform the sky, far enough to be safe. It would be a catastrophe for the star and a gift to science, a violent death delivered to Earth as light. But even this must be qualified. The brightness estimates depend on details of the explosion, dust, geometry, and distance. It may be comparable to the full moon. It may be somewhat dimmer or brighter. It may be visible in daylight for a period. It will not look like a second sun. It will be a brilliant point, not a disk filling the sky. There will be no shock wave reaching Earth in any meaningful destructive sense. The most powerful immediate arrival will be neutrinos, which will pass through us almost entirely, as if we were empty. The fact that billions or trillions of neutrinos could pass through your body during such an event and leave no sensation is itself a useful corrective. The universe can be overwhelming without being tactile. Immense events can cross you invisibly. Not every encounter with cosmic violence is experienced as damage. Sometimes it is experienced as data. That is what modern astronomy has become. The art of receiving distant violence as information. Light from hot plasma, spectral lines from atoms, neutrinos from collapsing cores, gravitational waves from merging compact objects, dust emission from cooling gas. The universe speaks through messengers, each carrying a different piece of the truth. Betelgeuse will be a multi-messenger event if it explodes, while humanity has the instruments to listen. This is another reason the timing matters. A supernova 10,000 years ago would have been seen and mythologized, but not measured. A supernova a million years from now might be observed by descendants or by no one. A supernova now, or within the technological lifetime of our species, would be captured with tools no earlier civilization possessed. We live in a narrow interval where we can both see the sky with ancient eyes and interrogate it with modern detectors. Betelgeuse is waiting in that interval with us, yet we should resist pretending it waits for us. It does not. It is not timed for our civilization. It is not an omen. It is not a message. The human meaning of Betelgeuse is real to humans, but the star's physics is indifferent. This is not a contradiction. Meaning can be local without being false. The star does not care that we look at it, but looking still changes us. Now look again at the red color. That color is not just aesthetic. It tells us the surface is cool compared with hotter blue stars. Cool, in this case, still means thousands of degrees. It tells us energy is spread over an enormous area. It tells us the star's outer envelope has expanded. Color becomes diagnosis. Beauty becomes evidence. Its variability is evidence too. Betelgeuse has a roughly 400-day pulsation cycle and longer variations as well. The star expands and contracts, brightens and dims, shifts with convective motion and surface structure. This irregularity is part of why it lives in public imagination. A steady star is easier to ignore. A changing star feels alive. But alive is the wrong category. Betelgeuse is not alive. It is dynamic. And perhaps that distinction matters because it prevents us from turning physics into mythology too quickly. The star does not struggle in any conscious sense. It does not know it is dying. It does not fight gravity. The language of struggle is ours. The mechanism is not. Still, metaphor has a role when it is honest about itself. Betelgeuse is like a giant breathing because its outer layers move. It is like a clock because its nuclear sequence is finite. It is like an ancestor because future matter may inherit its debris. It is like a warning because its state reveals the consequence of massive star evolution. None of these metaphors are literal. All can guide attention if they remain attached to mechanism. That is the skill of careful wonder. Allow the image, then return to the physics. The physics says Betelgeuse likely began in a star-forming region associated with Orion. It lived rapidly because of its mass. It left the main sequence. It became a red supergiant. It developed an enormous convective atmosphere. It loses mass. It will eventually form an iron core if it has not already advanced close to that state. Core collapse will produce a supernova. The remnant will likely be a neutron star, though details of fallback and mass loss leave some uncertainty. The explosion will enrich the surrounding medium. Earth will be safe. The timing is uncertain. That chain is powerful enough. It does not need false urgency. In fact, false urgency weakens the story because it gives observers an easy escape. If someone hears Betelgeuse will explode soon, and then learns soon might mean 100,000 years, they feel tricked. The honest version creates a deeper unease. The universe operates on timescales where soon can be true and irrelevant at once. We are not the measure of the star's timeline. That is the discomfort worth preserving. There is also a humility in the way Betelgeuse resists exact knowledge. It is one of the most famous stars in the sky, studied for generations, imaged directly, watched by amateurs and professionals, and still its fundamental parameters remain imperfectly constrained. We know an enormous amount. We do not know enough to predict the final date. This is not embarrassing. It is a reminder that proximity in the sky does not equal simplicity. The same humility should shape how we discuss recent claims that Betelgeuse may be in a late carbon-burning stage or closer to explosion than older models suggest. Those studies are interesting because they challenge conservative timelines. They use pulsation, luminosity, and stellar modeling to argue for a more advanced evolutionary state. But they are not final. Other researchers disagree or find different evolutionary stages. The proper stance is not to dismiss them or to sensationalize them. The proper stance is to say the question is open, the models are sensitive, and the star is important precisely because resolving this uncertainty will teach us about red supergiants. This is what real controversy looks like in science. Not one side saying it will explode tomorrow, and the other saying nothing is happening. The real debate is about model assumptions, distances, pulsation modes, mass loss history, internal mixing, companion effects, and how surface data maps onto core state. It is slower than a headline and more interesting than a headline. Now imagine the final observable sequence as it would be experienced by humanity. A neutrino alert arrives. At first, only scientists know what it means. Detectors in different parts of the world register a burst consistent with core collapse. The source localization points toward Orion. Messages go out automatically. Telescopes slew. Astronomers wait for light from a star that, for everyone else, still looks normal. For minutes or hours, the world may know that Betelgeuse has died before the sky shows it. That interval would be unlike anything in astronomical history. Foreknowledge of a visible stellar death. The star would still be there to the naked eye, a red point, but the instruments would have heard its core collapse. The public would look up at Orion and wait for a light that had already begun inside the star centuries earlier and had just reached the final hours of its journey through the envelope. Then the shock breaks out. The light rises. Spectra change hour by hour. The supernova blooms. At peak, it dominates the sky. People step outside in cities where only a handful of stars are usually visible and see a new point burning through light pollution. Rural observers see shadows. The moon has a rival for attention. For once, the entire planet shares an astronomical event not as an eclipse path or a meteor shower, but as a transformation in a familiar constellation. The science would be relentless. Early spectra would reveal the structure of the outer layers. Neutrino counts would test models of core collapse. Light curves would show how the shock deposits energy in the envelope. Radio and X-ray observations would track interaction with material Betelgeuse lost before the explosion. Infrared telescopes would watch dust form or be destroyed. Over years, the expanding remnant would become a new target. Over decades, it would become part of astronomical education. But outside the observatories, another transformation would occur. People would learn viscerally that the stars are not background. The sky can change. A point that seemed permanent can become an event. A constellation can lose a member. A myth can be edited by physics. And after the supernova fades, the absence may be as powerful as the brilliance. Betelgeuse's red glow will be gone. The shoulder of Orion will not look the same. The sky will have a scar. That scar will be useful. It will remind future observers that stability is partly a function of short memory. Humans call a thing permanent when it outlasts a few generations. The cosmos uses another scale. Betelgeuse has been stable enough for every civilization that named Orion, yet it is unstable on the timescale of stellar evolution. The difference between permanence and change is often the length of the observer's life. This is the quiet philosophical edge of the story. We do not live in a permanent universe. We live in a universe where many processes are simply slower than grief, slower than empire, slower than language. Betelgeuse happens to be a place where the slow process may become sudden enough for eyes to notice. The star also challenges a second assumption, that destruction is the opposite of creation. For a planet, a supernova nearby could be devastating. For a molecular cloud, supernova debris can become enrichment. For a future planetary system, those elements can become geology and biology. The moral category depends on the scale. The universe does not separate creation and destruction as cleanly as human stories do. This does not mean destruction is good. It means the universe is not built around our categories. A star's death can be catastrophic for anything nearby and necessary for complexity elsewhere. The same shock wave can tear apart and seed. The same explosion can erase a star and contribute to future worlds. Betelgeuse's future is not a simple tragedy. It is a violent transfer. That transfer connects directly to us. The iron in blood did not appear by gentle assembly in the early universe. The oxygen in breath was made by nuclear burning. The carbon in living chemistry was produced in stars and distributed through stellar winds and explosions. We are not made merely under the stars. We are made after stars. Betelgeuse is a living example of a process that predates us and will outlast us. There is a danger in saying this too beautifully. It can make supernovae sound as if they exist for life. They do not. Most stellar debris will never become a living world. Most enriched gas will drift, mix, form stars, or remain barren. The universe produces ingredients without promising recipes. Complexity is possible, not guaranteed. That correction is essential. Betelgeuse does not die so that life may exist. It dies because massive stars with iron cores collapse. Life, where it emerges, takes advantage of the materials such deaths make available. Purpose is not required. Consequence is enough. And perhaps consequence is more interesting than purpose. Purpose would make the universe smaller, more human, more obedient to our need for narrative. Consequence leaves the universe vast. A star dies for no reason we can call intention, and yet that death changes what can exist later. Meaning appears downstream, in observers who inherit the materials and ask questions. This is why looking at Betelgeuse can feel different after you understand it. At first it is a red star, then it becomes a giant, then it becomes a dying giant, then it becomes a hidden core, a future neutrino burst, a supernova, a remnant, a cloud of elements, a possible ancestor of future chemistry. The point of light deepens. It stops being a point. We should also remember that Betelgeuse is not the most massive star, not the most luminous star, not the nearest red supergiant in every useful sense, not necessarily the next to explode. Its fame comes from a combination of science and visibility. It is a bridge between naked eye astronomy and advanced stellar physics. That bridge is valuable because astronomy can become too abstract. A red point you can find without equipment keeps the discussion grounded. Step outside, and Orion does the rest. The belt is easy. The shoulder is visible. The color is obvious. You are not looking at a diagram. You are receiving photons that crossed centuries. They left a star whose surface was larger than the orbits of inner planets, passed through interstellar space, entered the atmosphere, scattered around city lights or crossed clean dark air, and ended as a signal in your retina. The scale is absurd, but the act is intimate. A dying star touches the chemistry of your eye. No telescope can improve on that feeling, though telescopes can explain it. The explanation does not remove the awe. It changes its texture. Before the science, the star is beautiful because it is bright and red. After the science, it is beautiful because the redness is evidence of expansion, because the brightness hides distance, because the distance hides time, because the calm point hides instability, because the instability hides creation. That is the kind of awe worth defending, not awe against knowledge, but awe produced by knowledge. At the end, Betelgeuse leaves us with a difficult balance. Do not panic. The star is not a danger to Earth. Do not dismiss it. It is one of the most important red supergiants we can study. Do not claim it will explode tomorrow. We do not know. Do not say it will not explode for 100,000 years, as if that is certain either. The model space is still debated. Do not treat the great dimming as proof of imminent death. It was likely dust and surface cooling. Do not treat the dust event as irrelevant. It teaches us how such stars lose mass. Do not reduce the star to spectacle. Do not drain it of drama. Betelgeuse deserves the harder middle. The harder middle says this: Betelgeuse is a late-stage massive star whose fate is clear, but whose timing is hidden. Its enormous size is not just a number. It is evidence of deep structural change. Its future supernova will be safe for Earth, but transformative for astronomy and culture. Its death will be violent, but that violence belongs to the same chain of process that made complex chemistry possible. The star is not warning us about our immediate doom. It is teaching us that the universe builds with explosions and remembers through matter. If you want fear, there is fear enough in that. Not fear of personal extinction by a nearby supernova, but fear of scale, of delay, of inevitability, of the fact that every familiar sky is temporary. If you want wonder, there is wonder enough too. A star visible to the naked eye contains a hidden nuclear history that leads from hydrogen to iron, from iron to collapse, from collapse to debris, from debris to future worlds. One day the red shoulder of Orion will change. Maybe no human alive now will see it. Maybe the signal is already on its way. Maybe a future civilization will watch. Maybe no one will. The event does not need us to occur. But if we are here when it happens, the universe will give us one of its rarest gifts, a visible lesson in impermanence. For a few weeks, the sky will be rewritten. Then the light will fade. The remnant will expand. The new elements will begin their slow migration into the interstellar medium. Orion will be altered. Human memory will absorb the event. Science will spend generations extracting meaning from the data. And somewhere far in the future, perhaps in a cloud not yet gathered, some fraction of Betelgeuse may become part of something colder, quieter, and more delicate than the star itself ever was. A rock, a sea, a molecule, a living cell, an eye. That possibility is not guaranteed. It is enough that it is allowed. So when you look up and find Betelgeuse, resist the cheap question. Do not ask only whether it will explode tomorrow. Ask what it means that a star can be both doomed and generative, both unstable and necessary, both already old and only millions of years young, both a point of light and a volume larger than planetary orbits. Ask what it means that the universe hides its decisive processes behind surfaces we cannot penetrate, then sends us late signals and asks us to reconstruct the story. The red light above Orion is not a countdown on a wall. It is a delayed confession from a star that burned too brightly to last. It tells us that size can be fragility, that brilliance can be expense, that death can scatter ingredients, and that the sky we inherit is not finished. Betelgeuse is still there, at least in the light reaching us now. Still red, still variable, still shedding, still concealing the state of its core beneath an atmosphere so vast that the orbit of Earth would be lost inside it. It may have thousands of years. It may have more. It may have less. But the path is set. The final physics will not ask permission from myth or calendar. When the core can no longer pay the debt of gravity, the giant will fall inward before it blows outward. A star large enough to swallow worlds will be defeated by a core smaller than a planet. The outer magnificence will depend on an inner point of failure. That is the final irony of Betelgeuse. The fate of an object larger than the inner solar system will be decided in a hidden center, on a scale the eye will never see. And then, after the collapse, after the neutrinos, after the shock, after the blaze, after the fading, the star will no longer be a red point in a hunter's shoulder. It will be a cloud, a remnant, a record of a massive star's life written in expanding gas. The sky will lose a familiar light and gain a new memory. That is not the end of Betelgeuse. It is the end of Betelgeuse as a star. In astronomy, those are different statements. The universe rarely preserves form. It preserves consequence. And for now, the consequence has not yet arrived. The old light continues to come. Night after night, century-old photons cross the last thin layer of air and fall into human eyes. We receive them casually, sometimes without knowing the name of the star that sent them. But inside those photons is a history of nuclear fire, swollen atmosphere, dust, uncertainty, and a future explosion held back by whatever fuel remains in the hidden core. A point of light can contain all of that. There is another reason the star deserves care rather than hype. A bad story about Betelgeuse makes astronomy smaller. It turns a physical system into a fortune cookie. Will it explode soon, yes or no? But a better story asks why the timing is difficult in the first place. It asks why a star we can see with unaided eyes can still keep its deepest state hidden. The answer is that stars are not transparent clocks. They are layered, convective, magnetized, rotating, mass-losing bodies. And each layer speaks a different language. The surface speaks in brightness. The atmosphere speaks in dust and spectral lines. The wind speaks in infrared shells. The core speaks only through models until the final neutrino burst. This is why the Great Dimming was so easy to misunderstand. It looked like a message from the core because it was dramatic. But drama is not location. A surface cloud can make a star look as if its whole engine is failing. A cool patch can change visible light while the deep center continues along a path that may have thousands of years left. The object that frightens us is often not the object we are actually measuring. We measured the face and imagined the heart. A fair skeptic might say that all this caution drains the story of urgency. If Betelgeuse is safe, if the dimming was dust, if the explosion may not happen for many human lifetimes, then why care now? The answer is that science is not only the study of immediate danger, it is the study of systems that define the conditions of existence. A nearby red supergiant does not need to threaten us to matter. It matters because it lets us watch the physics that made our own planet chemically possible. It matters because red supergiants are unstable in ways we still struggle to model. It matters because the final years before core collapse may be encoded in surface behavior we do not yet know how to read. It matters because the next galactic supernova will test physics from stellar evolution to neutrino transport to nucleosynthesis. Betelgeuse is not an emergency. It is a rehearsal for one of the rarest experiments nature can run in our neighborhood. Think about what an experiment like that would mean. Human beings cannot build a red supergiant. We cannot compress an iron core to nuclear density. We cannot create a neutrino burst with the energy of a collapsing star. We cannot make a shock wave fight through a stellar envelope hundreds of millions of kilometers wide. We wait for the universe to do it. Most of astronomy is like this. It is not laboratory control, but cosmic patience. We improve our detectors, refine our models, and hope that a star, somewhere close enough to observe, reaches the end while we are capable of paying attention. Betelgeuse is one candidate for that role, and its candidacy has cultural power because everyone can find it. A star hidden behind dust in the far side of the Milky Way may explode before it does, and neutrino detectors may notice what optical telescopes cannot. But Betelgeuse would be different. It would be public. It would not belong only to scientific instruments. It would belong to children in backyards, drivers on night roads, astronomers on mountain observatories, people in cities who rarely see more than a few stars. A nearby supernova in Orion would turn stellar death into a shared human experience. There is a responsibility in imagining that experience. We should not tell people they are in danger when they are not. We should not make the universe seem less trustworthy by inventing threats. The true universe is already strange enough. A safe supernova that can be seen in daylight is more remarkable than a fake apocalypse. A star that may already be gone in its own present while still glowing in ours is more haunting than a false warning about radiation. A future neutrino alarm that gives humanity a few hours before a visible explosion is more dramatic than the claim that the Great Dimming was a death sign, and the light itself will carry layers of history. If the explosion reaches Earth, the first photons we see from the supernova will not simply be new brightness. They will be the end of a journey that began when the shock escaped the star's surface. Before that visible breakout, the core had already collapsed. Before that collapse, iron had gathered. Before the iron, silicon burned. Before silicon, oxygen, neon, carbon, helium, and hydrogen each had their era. The light in the sky will be the final page of a book written in nuclear reactions. Without the earlier pages, the blaze means nothing. This is why the onion structure matters so much. It is not just a textbook diagram. It is the star's autobiography. The outer hydrogen envelope remembers the original fuel. The helium shell remembers the first ash. The deeper carbon and oxygen layers remember the star's second life. Neon, magnesium, silicon, sulfur, and iron mark the increasingly desperate attempts of gravity and fusion to maintain balance. By the time the iron core appears, the story has reached a sentence that cannot continue. Iron does not pay the energy debt, gravity collects. In ordinary life, we think of collapse as a failure of support. In a massive star, collapse is more like a transition between regimes of physics. Electrons resist until they cannot. Nuclei are broken. Protons and electrons become neutrons. Neutrinos stream out. Nuclear density appears. The inner core becomes an object governed by quantum rules, under conditions so extreme that human material intuition is almost useless. The explosion is not simply a big fire. It is the result of quantum mechanics, nuclear physics, gravity, fluid dynamics, and radiation transport colliding in a matter of seconds. This is why supernova models remain challenging, even though the broad mechanism is understood. The details depend on multidimensional turbulence, rotation, magnetic fields, neutrino heating, convection, fallback, and the structure of the progenitor star. A clean one-dimensional picture can teach the sequence, but real stars are not one-dimensional. Betelgeuse, with its enormous surface cells and lopsided brightness, reminds us of that. It will not die as a perfect sphere drawn on a chalkboard. It will die as a turbulent, asymmetric, mass-losing object whose final explosion may carry the fingerprints of all that messiness. The messiness is not a weakness in the story. It is the story. The universe does not owe us elegant endings. It produces events rich enough that even after a nearby supernova, scientists could spend lifetimes arguing about the details. How much mass was lost before collapse? Was there a companion shaping the outer atmosphere? Did the explosion leave a neutron star, or did fallback create a black hole? How strong was the magnetic field? How much dust formed in the remnant? Which elements were produced, and in what quantities? What did the early neutrino signal reveal about the proto-neutron star? These questions are not footnotes. They are the reason the explosion would matter scientifically. A nearby supernova would also teach us about our own detection systems. It would test whether the early warning network works under real conditions. It would test how quickly observatories can coordinate. It would test public communication under a sky event that millions can see and misunderstand. It would reveal whether we have learned to talk about uncertainty without flattening it into panic or boredom. In that sense, Betelgeuse is already testing us before it explodes. It tested us during the Great Dimming. We saw how fast curiosity can become rumor, and how patiently evidence had to pull the story back toward dust, temperature, and mass loss. There is a lesson there for every scientific controversy. The most dramatic explanation is not always wrong, but it must earn its place. A dimming star could be a sign of extraordinary internal change, but it can also be a cloud. A brightening could mean evolution, but it can also mean pulsation. A model suggesting a shorter timeline can be important, but it does not erase all other models. Science advances by letting the exciting possibility stand next to the boring correction until the data decides. Betelgeuse is a perfect arena for that discipline because it tempts us constantly toward the exciting possibility. This discipline does not reduce wonder. It protects it from collapse. If every unusual change becomes a prophecy, then the public eventually stops believing. If every uncertainty becomes a cliffhanger, the real cliffhangers lose force. Betelgeuse does not need inflated claims. It is already a star whose atmosphere may engulf or reach beyond the scale of planetary orbits, whose surface can be directly resolved despite hundreds of light-years of distance. Supergiant, whose core is advancing toward a physical limit that ends in collapse, and whose future death will be safe enough to watch and powerful enough to reshape a constellation. That is enough. There is also a deeper human reason to care. Betelgeuse shows us a form of mortality unlike our own. Human death is personal, biological, intimate. Stellar death is structural. A star dies because the mechanisms that held it together reach a boundary. It has no fear, no consciousness, no desire to continue. And yet we recognize something in the sequence. Energy spent, balance lost, layers exposed, center failing, outward appearance remaining calm while hidden support disappears. We should be careful not to anthropomorphize the star, but we should not pretend that metaphor is useless. Metaphor is how human minds cross the distance between plasma and meaning. The star's mortality also reflects backward onto the sun. The sun will not explode like Betelgeuse. It lacks the mass. It will not build an iron core or collapse into a neutron star. Its ending will be slower, swelling into a red giant, shedding outer layers, leaving a white dwarf. But seeing Betelgeuse helps us see that the sun, too, is temporary. The difference is not between mortal stars and immortal stars. It is between modes of ending. Some stars rage. Some stars fade. None remain unchanged forever. That knowledge can make the sky feel less like a ceiling and more like a process. The constellations stop being decorations and become snapshots of different phases of stellar life. Blue stars burning fast, red giants swelling, white dwarfs cooling, nebulae forming, clusters dispersing, remnants spinning. The night sky is not a painted dome. It is a slow catastrophe and a slow creation happening at once. Betelgeuse is one of the places where that truth becomes visible. There is one more temptation we should name before leaving the star. The temptation to think that because Betelgeuse is famous, it must be simple. Famous objects often become simplified objects. We turn Saturn into rings, Mars into red dust, black holes into drains, and Betelgeuse into the star that might explode. But a famous star can still be scientifically difficult. Its distance has been refined and debated. Its radius changes with method and wavelength. Its atmosphere is extended enough that the word surface becomes approximate. Its long-period variability may involve pulsation, convection, dust, and perhaps a companion. Its core state must be inferred from models rather than directly seen. Fame gives us a name, not mastery. That is why Betelgeuse is useful as a test of intellectual honesty. Can we love a spectacular object without forcing it to be simpler than it is? Can we admit that the safest statement is not always the most clickable one? Can we say that the star will explode, that it may do so sooner than conservative estimates suggest, that it may also remain red and restless for many millennia, and that all three statements can belong to the same honest scientific picture? The answer matters beyond this one star. It is how science should sound when it meets the public. Vivid enough to be remembered, careful enough to be trusted. The best version of wonder does not ask us to abandon precision. It asks us to notice that precision often makes the wonder deeper. A full moon brightness estimate is better than a vague claim of blinding light. A danger zone measured in tens of light years is more reassuring than empty comfort. A neutrino warning measured in minutes or hours is more thrilling than fantasy. A dust cloud explanation for the great dimming is more beautiful than a false omen, because it means we watched stardust form close to the face of a dying giant. Reality does not become smaller when we remove exaggeration. It becomes sharper. This is why Betelgeuse matters. Not because it is the biggest star, not because it is a danger, not because it gives us permission to predict a spectacle on command. It matters because it compresses the entire drama of massive star evolution into something visible from a sidewalk. It lets anyone, with no telescope and no special equipment, look directly at a star that has nearly finished spending the fuel of its life. The next time Orion rises, the red shoulder may look unchanged. It may look unchanged for generations. That does not make the story less real. A fuse can be long and still be burning. A star can appear calm and still be evolving toward collapse. A message can travel centuries and still arrive suddenly. The sky is not silent because nothing is happening. It is silent because most of what is happening is too large, too slow, too far, or too deeply buried for human senses. Betelgeuse gives us a rare exception, a distant process close enough to name, bright enough to watch, unstable enough to study, and inevitable enough to humble us. Look at it while it is still there. Not because it will vanish tonight, but because nothing in the sky is obliged to remain forever. Betelgeuse is a dying giant, a chemical ancestor, a variable star, a future supernova, a scientific argument, and a reminder that the universe does not separate beauty from violence as neatly as we do. It glows red in Orion, not as a promise of disaster, but as evidence of a truth older than humanity. The cosmos makes the future out of things that cannot last, and that sharpness is the difference between a rumor and a revelation. Betelgeuse does not need to be exaggerated. It only needs to be understood, completely, patiently, honestly.